Section 8.4, trig substitution. This is similar to U substitution, but as you can imagine, we're going to be using trig functions. The whole key to this section is our Pythagorean identity, and we're going to use the Pythagorean identity in these three forms. Cosine squared is 1 minus sine squared. Secant squared is 1 plus tangent squared, and tangent squared is secant squared minus 1. Okay, so when do we use trig substitution? That's really the big question. We will use trig substitution when we see combinations of squares and square roots. And there will be three different situations. If we see square root of a squared minus u squared in our integral, then our substitution will be u equals a sine theta. And what's going to happen here, let's plug this in and see what happens. This gives us square root of a squared minus a squared sine squared theta. I can factor the a squared out. That's a squared times 1 minus cosine squared theta. And here's where, I'm sorry, 1 minus sine squared theta. I was getting ahead of myself. You can see where our trig identity comes in now. 1 minus sine squared is cosine squared. So this becomes square root of a squared cosine squared theta, which is a cosine theta. So this is the whole idea behind trig substitution. We're starting with square roots and squares. We're going to make a substitution to make the square root and the squares go away. Okay, the other two are similar. If you have square root of a squared plus u squared, then we're into this situation, a squared plus u squared. So in this situation, u is going to be a tangent theta. And pretty much the exact same thing happens. Let's work this out. Square root of a squared plus a squared tangent squared theta. You factor the a squared out. That's a squared times 1 plus tangent squared theta. 1 plus tangent squared, that's secant squared. So this is square root of a squared secant squared theta, which is a secant theta. All right, and then finally, the third possible situation, label these 1, 2, 3. If you have square root of u squared minus a squared, u squared minus a squared, u is going to be a secant theta. In which case, this square root will be a squared secant squared theta minus a squared. Factor the a squared out. Secant squared theta minus 1. Secant squared theta minus 1. Tangent squared. Square root of a squared tangent squared theta, which is a tangent theta. All right, so that's going to be the idea behind these trig substitutions. We're going to make the appropriate substitution so that we eliminate the combination of the square and the square root. All right, makes more sense when we actually do some examples. So let me grab some out of the book here. We'll start with one of each kind, I suppose. So let's say we have the integral of 4 over x squared square root of 16 minus x squared dx. Okay, first thing to note is that u substitution would not work. If you were going to do traditional u substitution, u would be the 16 minus x squared. du would be minus 2x. I don't have a minus 2x, so it's not going to work. We see that we have the combination of a square root and a square. We see it fits into pattern number 1, a squared minus u squared. So x in this case is going to be 4 sine theta. Now when we make our substitution, we also got to get rid of the dx. Dx is 4 cosine theta d theta. And then you can either memorize what's going to happen here, or write it on your formula card if you have space, I suppose. But I tend to not do that. I tend to just work it out. I tend to just write down square root of 16 minus 16 sine squared theta, and I factor the 16 out, and I see I have 1 minus sine squared, that's cosine squared, so that's going to be 4 cosine theta. So I tend to write it out that way. Like I say, you can write this on your formula card and know how these are going to come out for each one. Up to you. All right, so we make our substitutions. We have integral 4 over x squared. X squared is 16 sine squared theta. This square root down on bottom came out to be 4 cosine theta. And then our dx is 4 cosine theta d theta. All right, well, some reduction happens, which is nice. Those go with that. That goes with that. So I can write this as integral. I'm going to take 1/4 out front from that 4 and 16. 1 over sine squared theta d theta. And here's what happens. We're left with integrals that involve powers of trig. This one I would write as 1/4 integral cosecant squared theta d theta. And the good news is that happens to be one I know, because I know the derivative of cotangent is negative cosecant squared, which tells me the integral of cosecant squared is negative cotangent. So this is negative 1/4 cotangent theta plus c. Now, here's the bad news. The bad news is we're not done, because we started with x's. We should end with x's. We don't have x's, we have thetas. So here's what you have to do. You have to come back to here, and I'm going to write sine theta is x over 4. And then I'm going to draw a triangle. A right triangle. There's my angle theta. Sine is opposite over hypotenuse. And then I use the Pythagorean theorem. If I use the Pythagorean theorem, I would have solving. This would be square root of 16 minus x squared. So, final answer is negative 1/4. Looking at my triangle, cotangent is adjacent over opposite. So that's times square root of 16 minus x squared over x plus c. All right, so there's quite a bit that goes into these problems. First, you've got to make your substitutions. And there's quite a bit more there than there is just for a standard U substitution. Then you get your power of trig integrals. So we got to go back and remember how we did those power of trig ones. And then finally, you got to get your x's back in. All right, let's try a couple more here. How about the integral of x cubed over square root of x squared minus 25 dx. Again, traditional u substitution doesn't work. You would let u be the x squared minus 125. Du would be 2x. Doesn't match the x cubed you have there. The thing to notice is you have a square root and a square. All right, this one fits into pattern number 3, x squared minus a squared. So x is a secant theta. X is 5 secant theta, which means dx is 5, the derivative of secant is secant theta tangent theta d theta. And then again, I've got to work this out. So square root of this bottom is going to be square root of 25 secant squared theta minus 25. That's 25 tangent squared theta with a square root over the whole thing. So that's 5 tangent theta. All right, plug it all in. This becomes integral. X cubed, 5 cubed is 125 secant cubed theta divided by the square root, turned out to be 5 tangent theta, and then dx was 5 secant theta tangent theta d theta. All right, again, some reduction happens. The 5 with the 5, the tangent with the tangent. We're left with 125 integral secant to the 4th theta d theta. All right, now what do we do when we have secant to the 4th? We have secant with an even power. We remember that the derivative of tangent is secant squared. So it seems like we want to keep a secant squared and convert everything else. So I'm going to write this as 125 integral secant squared theta times secant squared theta d theta, which is 125 integral secant squared theta times, got to remember your identity here, secant squared is 1 plus tangent squared theta d theta. So now we have a u substitution. U is tangent theta, which means du is secant squared theta d theta. So we have 125 integral 1 plus u squared du. So that's 125 times u plus 1/3 u cubed plus c. Got to plug our thetas back in. 125 tangent theta plus 1/3 tangent cubed theta plus c. And almost there. Now we got to plug our x's back in. So we come way back up here. Secant theta is x over 5. So draw a triangle. Secant is x over 5. That's hypotenuse over adjacent. So using the Pythagorean identity, solve this. You get x squared minus 25. And so, final answer, 125 times tangent is square root of x squared minus 25 over 5 plus 1/3 times square root of x squared minus 25 over 5, whole thing cubed, plus c. All right, I've only got about 10 seconds left because my videos can only be 15 minutes long with this software. So I'm going to pause, and then I'll start a new video, and we'll do some more problems.